Okay, so yeah, so if you want me to be full screen, you need to just pin my video or something. I don't do the share screen thing. So yeah, so thanks for the kind introduction. Just a quick overview of my lab. We cover really the three themes that you mentioned: learning perceptual representations, reasoning about uncertainty, and training robots and simulators. And so today I'm really just going to talk about the third theme, which is how can we endow robots with some kind of learning capability in a simulation environment and then transfer that to the real robot hardware. So obviously we want robots that learn. This is clear, but what's not clear is kind of everything else, right? How to teach them is not straightforward. So in this video, what we're showing is a human demonstrator had to show the rough idea of how to do a task of swinging this ball up into this cup. So maybe we need to give demonstrations. Maybe we need to write a reward function. Some combination of these two things are possible tools that we can use to help robots learn. The problem is that doing things on real robot hardware is really slow, it's really expensive, it's really dangerous, and it can be really tedious. So this is an example of a massive project undertaken by the Google Research Lab, where they had, I don't know, I think 16 or so of these arms that ran continuously, more or less, for a period of like 3 to 4 months. And we're trying to undertake the task of learning to pick and place. And so, I mean, obviously just setting up this lab is like incredibly expensive, and still it took them 3 months, these robots, to learn how to do basic pick and place. So an intuitive solution to this problem is that we want to learn in simulation. It's still time consuming to build a simulator, and the simulator will never look exactly like reality, but nevertheless, we've seen actually amazing capabilities that have been learned primarily in simulation and then deployed on real robots. An amazing example is this one that I'm showing on the right, where this robot hand learned to solve the Rubik's Cube with one hand, and the like solving of which like moves to make in the Rubik's Cube is not particularly difficult, but what's tremendously difficult is modeling all of the forces and contacts between the cube and the hand with so much dexterity in the hand and so many contact points. And like the building of this simulator was, you know, in some ways as hard of an engineering problem as actually solving the task on the real robot. And so it's not necessarily clear how much effort we should put into building these very, very high fidelity simulators versus how much time we should spend actually just training on the robot in the real world. And since this is an RL seminar, I thought I would speak specifically to the case of sim to real and RL for robotics. So obviously, RL tends to be particularly sample inefficient when it comes to algorithms for learning agents. So it is especially appealing to employ RL in a simulator first, where we can have many samples and then transfer that agent either in a 0 shot, where you do no experiments on the robot, or in some few shot setting, where you only have to do a few rollouts on the robot. However, there are some important limitations to consider that are specific to the case of using RL on robots and don't necessarily apply to all the other situations where RL has had tremendous success. The first thing to consider is that there's this implicit notion in the modeling of the environment as a Markov decision process that says that the environment is going to provide you with a reward. But the real world doesn't always provide you with this reward. For example, if I'm trying to get a car to drive down the road, there's no magical reward signal that's going to be given to me if my robot makes progress down the road. Similarly, there's no magic cost that's going to be given to my robot if it does something wrong. So as a result, ideally, we want 0 shot transfer. That means that we can have all of the training happen in a simulator where we have access to privileged information and can craft these reward functions, and none of the fine tuning to happen. But this is more challenging. A second limitation is that the environment doesn't magically reset itself. So in the example of the ball getting rolled up into the cup, that was an example of an environment that does reset itself. And it was like that task, I'm sure, was explicitly chosen because of that property. But in general, it's not like when an episode ends that we magically go back to some randomly initialized starting conditions and can start over. And then most importantly, maybe for these tasks like autonomous driving, is that we need safety, but not just of the final policy, we need safety throughout the entire learning process. So as soon as we deploy the agent on the real hardware, we want to be able to at least guarantee that it's safe. So I like to think of the value of data, particularly with respect to RL, and that the different sources that you can get of data have different values. So first, maybe is simulated data. We can build a simulation, and we can roll out the robot in the simulated environment and get data, and this is relatively cheap. We might also be able to get off-policy rollouts, like, for example, in the case of autonomous driving, we might have all the data that's collected from all the cars in our fleet, and we might be able to use this, but this is not necessarily inside the learning process of an RL agent. And then finally, we have these on-policy rollouts, which are like the gold that we really want, because that's our agent rolling out our current best policy, and then we can actually like use the performance of that agent rollout to maximally inform how we should adjust that policy. And so there's this inverse relationship between how useful each of these data sources are for training and how easy they are to get. And I'll make one other note here, which is that not all simulations are actually equally as useful. Like a very low fidelity simulator might be really, really easy to get data from, but might not be particularly useful. So with that in mind, the outline for the rest of the talk is follows. I'm actually going to start with a sort of thought process that I would say is like, of all of these, the least well thought out. But I started thinking actually explicitly about this question of how we can assess the value of a simulator for a robot. Like, how do we even put a number on that, or how can we even quantify that? Then I'll talk about how we can, so I'll talk about two different sort of fundamental paradigms for how we can cross this gap from the simulator to the real world. One is that we're going to learn how to explicitly transfer from one data domain to the other. And then the second option is that we're going to learn a policy in the source domain, i.e. the simulator, that is able to just generalize out of the box. And I'm going to show some other extensions of this approach. And then finally, I'll talk about this AI Driving Olympics benchmark, which we've been hosting for a couple of years at top machine learning and robotics conferences. By the way, I don't know how the Q&A and everything like that's supposed to work, but I really don't mind getting interrupted in the middle if there's any questions, whoever wants to moderate that. Okay, so let's think about the value of a simulator. How can we actually put some kind of a number on the value of a simulator? Well, like roboticists have had this sort of very ambivalent relationship with simulators. Famously, Rodney Brooks, who is the former head of CSAIL, where I worked, quipped that simulators are doomed to succeed, meaning that your simulator is, you're always going to be able to overfit to your simulator, and it's going to give you overconfidence about how good you are actually doing on the real task. This statement was made before simulators were really a tool for learning. I mean, I think at this point, they were really a tool for verification of algorithms. And now I think we need to kind of like rethink this, this sort of mentality, right? So let's set up the problem. And this is kind of like a nice introduction to everything that we're going to talk about here. So as I'm sure you are all probably aware, in the real world, on one hand, we have this thing that we can design, which we call an agent. And on the other side, we have this thing that we treat as an untouchable, which is the environment. So in the robotic setup and in any MDP setup, basically, the agent can control the environment through control commands, which actually move actuators and cause the environment to change. Conversely, the agent can observe the world through sensors that give it possibly imperfect information about the environment. And this comes to the agent in the form of observations. In the simulation case, there's a strict one-to-one mapping between these elements. The agent is actually exactly the same, and that's really what we want, is we want this agent that can operate in both regimes. This environment is replaced by an environment model. So what do I mean by the environment here? I mean, if it's an autonomous driving setting, you have to model how the other agents are going to behave. You have to model how the pedestrians are going to behave. You have to model how things look. You have to model the physical parameters about other things. So these are all things that are comprised inside the model. Instead of there being real actuators, now we model the dynamics of the actors that exist in this environment model. And we keep the API the same. So we issue these control commands, and then we use these dynamics equations to update the environment model. On the other hand, we observe the environment now not directly through sensors, but through some kind of rendering agent. And so the issue here, okay, and our objective is to learn in simulation as much as we can, and then be able to transfer that agent to the real world. And the way that we evaluate how well we're doing is on some task. And we have some kind of set of metrics that tell us how we're doing in that task. In reinforcement learning terms, this is usually equivalent to the reward function. And if we can evaluate that task, we can feed that performance back to the agent if possible, and then we can refine our agent over time. Okay, so the issue in the case of this sim-to-real problem is that I argue that there's actually a reality gap that is induced in each single one of these equivalences. So the actuation and the dynamics are going to be imperfect. The model of the way that things exist in the world is going to be imperfect. And our rendering is not going to be exactly the way that it would be in simulation. And what's worse is that these gaps are actually going to compound. It's not like they're going to combine in some simplistic way. Like if I get the dynamics wrong, that's going to cause something wrong to happen in the environment, and that's going to cause what I sense to be wrong. And all these things are just going to get worse and worse. But so let's take like a really naive stab at how we would evaluate this reality gap. So the first thing that you might think to do was, okay, let's take some actuation values and let's feed the exact same actuation to both the dynamics model in the simulator case and the real system through the actuators. And let's look at what we get at the output. So we're going to get some rendered output in the case of the simulation, and we're going to get some real data log in the case of the real robot. So why don't we just take those two and just see the difference between them, right? So we can just evaluate, say, the pixel-wise L2 loss between this stream of data. So I argue that this is the wrong way to evaluate really this reality gap. And there's kind of, it leaves me with more questions than answers. So question one is, we really don't understand out of which of the three reality gaps has caused this discrepancy between the real data. Is this just because of rendering? Is our dynamics wrong? Or is our model completely wrong? Like, we really have no idea where to go next after we get this number. Question two is, I would ask, is that I'm not really sure that we need real world fidelity to solve a lot of the tasks that we want to solve with ARL. For example, in this example that I'm showing, like, what's happening in the background is irrelevant, right? What we need to get right is the dynamics of the robot and maybe how the road scene looks. But it's possible that whatever happens in the background is not important. And thirdly, just doing this pixel-wise comparison says nothing about what this simulator's value is as a tool for learning, for teaching a learning agent. So I propose that we decouple the value of a simulator into two components. One is, how faithful is it as a predictor of reality? And the other is, how useful is it as a teacher of learning agents? And I think that we can, by decoupling things this way, we can write down actual metrics for each of these two cases. So in the first case, considering the simulator as a predictor, well, I argue that we actually don't care about the pixel-wise difference between the sensor output. What we really care is, how good is it at predicting the value in the metric that we actually care about for the task. So I call this thing the predictive reality gap. And it's quantified by the discrepancy in the performance on a specific task. So now we have this metric that's actually conditioned on a task. And I think that makes complete sense. Like if what you care about is driving the robot down the road, then what you care about when you're designing your simulator is that, that whatever your agent says that however far you drove down the road in simulation, if you do the same thing in the real world, you'll drive down the same amount of road or whatever. Moreover, I would argue that since we might not even care in some cases about the global value of the performance on these metrics, we might actually only care about the relative value on these metrics. And so an easier, perhaps, value to calculate, or maybe a more meaningful value, is actually the discrepancy in the partial ordering of a set of agents on a specified task. So basically, what I'm arguing here is that if in simulation we deem that agent A is better than agent B on metric I, and we evaluate those agents also on the real robot hardware, and indeed agent A is better than agent B on metric I, then we have a faithful reproduction of the relative performance of these two agents in the simulator. Okay, so part two is the simulator as a teacher. So really what we care about here is what I call the learning reality gap. And here there's sort of several ways that you can do this, and I haven't really been able to reason one over the other, but I give you one instance here. Let's say this learning reality gap is the number of trials that you need to do on a real robot for an agent that's trained in simulation to convergence to achieve a performance at least as good as if it had been trained on the entirely on the real robot. So effectively what we're trying to quantify here is how many runs on the real robot did we save by training in simulation first. So I actually don't have much more to say about this. We're in the midst of actually running some really cool experiments to see if we can, like how faithfully we can, these metrics actually translate to a better performance in practice. And so stay tuned on that one. But I sort of put this first because I think it's like a nice intro to like the rest of the talk. Okay, so let's assume now that we have a simulator. And I talked about these two options of ways that we can, for a learning agent, the way that we can train in simulation and then deploy in the real world. And so those two options are, one, we're going to learn how to transfer from the source domain, i.e. the simulator domain, to the real robot domain. And then the second option is that we're going to learn to just generalize and be robust. So the key idea here is that we want to learn a representation that is invariant to the domain shift between real and simulation. And we want to learn a representation that's also good for planning, or that jives with ARL, basically. So we're going to borrow some ideas, and I'm going to cover these sort of background ideas first. So the first idea is this idea of so-called adversarial discriminative transfer. So the idea here is that the first thing we're going to do is we're going to train a source encoder with supervised learning. So it doesn't necessarily matter what the task is too much right now, but in this example of the paper that I cite below, the task that they're considering is object pose regression. So in the simulator, you can assume that you have access to ground truth data, and that you can learn some kind of source encoding from image space to whatever the value is that you want to regress with supervised learning. So this is just a supervised learning problem. We're just going to regress this. Once we've done this in simulation, we're going to freeze this source encoder. And step two is we're going to basically formulate this as a GAN problem, where we're going to jointly train a target encoder that takes real data and a discriminator so that this target encoder is incentivized to produce embeddings that are indistinguishable by the discriminator as to whether they came from the source domain or whether they came from the target domain. So all we need as a prerequisite for this is a bunch of unlabeled, off-policy target data. So notice that we don't actually, at this point, we don't actually need to do any supervision. So we've just got a bucket of data from the simulator and a bucket of data from the real, and now we can train this, this target encoder in this GAN setup. And then step 3 is if we have a little bit of data from the target domain, we can fine tune the target encoder and the target regressor using a small number of examples from the target domain. So this is the sort of 3-step approach. We're going to train the source encoder, freeze it, use a GAN to train the target encoder, and then fine tune the target encoder with any small amount of the data that we have with the supervised learning loss. So this is fine for just a straight up perception problem, but it's sort of unclear, how we still have to do the planning downstream. So we need something that jives with this in terms of a planning model. And so what we propose to use here is this so-called universal planning networks, which is a framework which I really like a lot. I'll try and explain it to you. So these OT and OG are the current observation from your agent and the goal observation. And so the objective here is we're trying to plan a path that is a visual servoing kind of path where we get the target observation to line up with the goal observation. That's how we're going to define success. So the way that we do that is we have some encoder that's here described by F, parameterized by phi, that takes us to some latent space, X. Then we have some dynamics model, which takes us from xt to xt plus 1. And so we progress through this dynamics model for, say, capital T time steps. And then we want our embeddings, the embedding of the target that's been fed forward, to be as close as possible to the embedding of the goal. And we can do this planning process with just simple gradient descent, where we use the planning loss to find the actions that move us in latent space as close as possible to the target embedding. Once we get this sequence of actions, we feed them out into this outer loop where we have some expert trajectories, and we compare the action sequence that we found with whatever the expert trajectory sequence was. And this imitation loss is what we use to actually train the encoder and the dynamics model. So effectively, what we're going to do here is we're going to kind of plug these two ideas together. So we're going to take our simulated image and our goal image, and we're going to embed them. And we're going to start by doing this completely in the simulation setting, where we can generate as much data for imitation as we want. We have like some perfect policy or whatever in the simulator, or it could be expert trajectories that are really easy to get. And so we run this entire loop inside as the step 1 of the adversarial discriminative transfer. Then in step 2, we need a bucket of real data. Well, it just so happens in the case that we're considering, which is our Duckietown setup, that we have lots and lots of real data logs, and we can easily train a discriminator jointly with our target encoder to get this new target encoding. And then as long as we have a couple of real demos from the real robot, we can use those just to fine tune our target encoding and our planner in the real world. And so this is kind of a video of this thing working on this Duckietown setup, which is a low-cost robotic setup that we use. So step 1 is that, so this is what the simulator looks like. On the left, we have the simulation, and on the right, maybe we have some real data. So we do a whole bunch of data collection and simulation. And the way that the task that we're trying to do here is just to get the robot to drive down the lane. And so the goal observation here is just the observation that you would get from the robot if it was in the middle of the lane going straight. And so we execute a whole bunch of trajectories of it just going down the lane straight. So here, what Zihan's doing is he's perturbing the initial pose by an angle and an offset, and collecting a few expert trajectories of how you recover from those situations. And then we do the same in the simulator with much more easily. And then we can deploy on the real robot using this setup. So when we deploy on this setup without using our adversarial transfer idea, things don't go well. But you can see now that when we deploy it on the real robot setup, that we're able to recover from poor initializations and able to follow the road. And we have some graphs, some requisite graphs that show the performance of this method compared to a baseline where we don't do any domain transfer. Okay, so that's option one, learning to transfer. And so really the key idea here is that we want to learn an embedding that is invariant to the domain, whether it be the source domain or the target domain, and we want to learn a mapping, from that in that embedding space from one domain to the other. Okay, so option two is that we don't want to actually learn the mapping from one domain to the other. We just want to learn completely in simulation, and then we want to end up being robust. So the key idea here is that, well, so the underlying problem is that some of the parameters in the simulator are wrong, and so for those parameters that we aren't sure about, we're just going to randomize over them. This is not a particularly new idea, but what we want is that we want the simulator to propose simulation instances that are the most useful, that are going to encourage the best generalization. And really, I think the underlying kind of like cool idea that I still think could be further explored is that this idea that in RL we have this sort of very agent-centric view that like the agent is something that learns and the environment is something that is external and static. But in this world, you can also kind of think of the simulator as being an agent in and of itself, where the simulator is incentivized or rewarded by teaching the agent. And so we sort of get very quickly here to like a kind of curriculum learning kind of idea here. A little bit of background. So as I mentioned, what we're going to consider now is the simulator is a mapping from some parameters to a simulation instance. And the idea behind this domain randomization thing is that for all the things that we don't care about, so on the left, all the background, color, all the shape of these hoops, everything like that, we're just going to randomize over them because we assume that we don't know them. And then the hope is that when we deploy the agent on the real robot, that the agent is going to view the real world as just another variation that's very similar to all the variations that it saw in simulation. And that we somehow distilled what's important about the task as the things that don't vary in the simulator, and that the agent can become robust to the variations in the things that we don't care about, but pays attention to the semantics or the things that we do care about. So this is idea. This is not my work. This is a Davide Scaramuza work in quadrotor navigation. And so we can write this down as an algorithm. I don't want to go too much into the weeds here, but so just to walk through this, the input here is some randomization space that we're going to randomize our parameters over. And this simulator S, which is actually a function that generates simulator instances. We have to initialize our policy somehow. And then this big T rand is going to be our collection of all these trajectories. And so at each episode T, the first thing that we do is we sample over all of the possible parameters that we have. And so here I've denoted those by psi, and the big U there denotes just like a uniform sampling between inside the ranges of these parameters, low and high. And then once we've sampled this, then we can generate an environment, generate a simulation instance that we can use to generate a rollout. So we generate a trajectory, we add that trajectory to our replay buffer, and then we take, at some point we take a policy step using our replay buffer, using a typical policy gradient. So, I mean, I think the limitation here is that sampling just uniformly from this parameter space may or may not be the right strategy for sampling. And so the question that we were interested to answer here is really how to pick which samples are the best samples to train on. In other words, which simulation instances are the most useful. And the answer to this is really to think about the simulator as an agent, and we end up with this sort of like outer loop RL, this outer RL loop that operates over the simulator that's teaching the inner loop agent. So another quick bit of background on the algorithm. not that this is like particularly important to understand the very nitty-gritty details, but we employed this. So the problem is that modeling this thing in very high dimensional, like modeling this outer loop thing as an agent where you're randomizing over simulation parameters is very high dimensional and possibly like difficult to model. And so we leverage this tool called Stein Variational Policy Gradient. So how does this work? Well, it's built off of this idea of Stein Variational Gradient Descent, which effectively performs variational inference by approximating a target distribution as a set of particles. So we don't have a target distribution in the case of RL, but what we can do is we can leverage the same sort of idea to learn an ensemble of policies, we call mu parametrized by phi, in some kind of maximum entropy RL framework. And so this Stein variational gradient descent, what this bottom equation is showing is just the update rule for the particles. So for each particle, at each time step, we update them using some mixture of the gradient of the cost function and then the gradient with respect to some kernel, where this kernel is sort of like a hyperparameter that controls the repulsion or attraction of these particles in the particle set. So with this in mind, the final algorithm flow looks something like this. So we have this simulator at the top, which consumes parameters and generates simulator instances. And then we assume that we have some reference policy, some reference environment, A, on which our policy performs well. This is like some canonical like reference environment. Maybe we've already trained our policy on it. And so if our simulator generates simulation instances, if we roll out our policy in those simulation environments, and the output is very, very different than what we got in the reference environment, then our intuition is that that's a good clue that we should train on that environment more. In other words, if we got something very, very different than what we got in the reference environment, it's likely that our policy is not performing very well in that simulation instance, and therefore we should allocate more learning bandwidth to that simulation instance. And so the way that this is enforced is through this discriminator. So if the discriminator cannot tell the difference between the reference environment rollout and the simulation instance rollout, then the reward is very low. But if it can tell the difference, then the reward is very high. And this then informs the SVG particles, which now try to navigate towards parts of the parameter space where they get the highest reward. And so the big, algorithm looks something like this, which is just a modification of the uniform case. So here, the main difference is that on line, let's see. So on line 6 now, we're running this loop for each SVG particle. For each particle, we get a set of parameters that we can generate a simulation instance. And then in line 13, for each one of the, so we roll out the policy in each one of these simulation instances. And then in line 13, we can calculate a reward associated with each one of these, which is just the output, the log likelihood of the output given from the discriminator. And then these are the rewards that are used to update our policy. And then we finally do the big SVPG update to update our particles. So in practice, this looks something like this. So we first tested this on this environment. It's called Lunar Lander. Probably some of you know it. So there's two actuation inputs. One is the mean engine strength, which shoots down. And one is the sideways engine strength, which goes sideways. And so we randomize the environment over the main engine strength, which is the one that goes down. And intuitively, you would expect that harder environments are environments where the main engine strength is lower, because it's harder to control this agent when you don't have as much actuation authority. And so what the top graph on the right here is showing is the generalization performance of our method in light blue compared to all the other methods. And you can see that our method is able to generalize better into these low engine strengths. And what I show in the bottom right is actually like the histogram of the number of times each main engine strength was chosen as a simulation instance by the SBPG particles. And you can see, and it's sort of time-stamped over time. So if you stare at this thing, what it shows you is that at the beginning, a roughly uniform sample of all the different engine strengths was taken. But over time, the algorithm learns that it needs to spend more and more effort to solve the environments with very low engine strength. And so in the like final, say 20% or 30% of the rollouts, almost exclusively they're allocated towards the very low engine strength case. Okay, so what about the real robot fine-tuning case? So, I mean, so we could take this agent and we could hope that it would generalize and we could put it on. And I think there is good reason to believe that it would generalize. But just like the previous case, it's possible that we also have access to some off-policy data. So assuming that we do have access to some off-policy data, we can do this kind of really clever trick that my student came up with. So instead now of this reference environment, we can just replace that reference environment that's, the reference environment that's generating the trajectories with just the real robot trajectories. And then we can actually just invert the reward. And so what this is going to do is so say we pre-trained this entire model on all of these instances from simulation. Well, if we want to do a little bit of fine tuning at the end, we actually want to, for a particular robot, we want to find the simulation instances that produce outputs that are as close to the real robot trajectories as we possibly can make them. And so now what we want is actually the discriminator to not be able to distinguish between the instances that are coming out, that are executed by the policy and the ones that were created by the real robot. And so in this way, just like the last time, we actually have a method that we can use to fine-tune the policy with off-policy real robot data. And so I show some results. This is with, so here we have a sort of a 2D, it's like a 2D plane example of a robot pushing a puck, where we can vary the friction between the puck and the table. And we show that our algorithm, say in the bottom right, is able to achieve better generalization performance than just uniformly sampling this friction. And the nice thing about this setup is that we can also do the real thing in real world, like we can actually change the parameters of the table or the properties of a table so that it slides more or less. And then this is a similar example where we have a very low-cost robot that's trying to reach to a point in space. So I just wanted to mention a couple of extensions to this framework, because I think it's actually kind of a powerful framework. Maybe one criticism of it, well, I'll get to that in a second. So the first thing that we can do is we can actually put this within a meta-learning framework. And so we can keep the entire pipeline the same, except in a meta-learning context, you can intuitively think that harder tasks are going to cause more adaptation. And so now we're trying to look for tasks, the SVPG particles are trying to look for tasks in a meta-learning context that cause the maximum discrepancy between the pre-adaptation and the post-adaptation rollouts, with the intuition being that if we had a lot of adaptation between pre and post, then that's a harder task that we should allocate more learning bandwidth to. And then finally, like I never particularly liked this idea that the entire curriculum was sort of being controlled by this discriminator and how calibrated the output of that discriminator was. So another modification that we can make to this is actually use this idea of a self-play framework. So I won't go too much into the details here, but we have now this, it's sort of the extension of the treatment of the environment setter as an agent. So here we have the environment setter Alice, and then the learner agent Bob. And so the reward functions that guide these two agents are shown on the right. RA is Alice's and RB is Bob's. And so Alice is incentivized to find tasks that she can solve really quickly, but that it takes Bob a long time to solve. And then Bob is incentivized to just solve tasks as fast as he possibly can. So this is enforced through this TB minus TA function in Alice's reward. And so now I think this kind of an idea actually has the potential to explicitly enforce a curriculum that guides the learner in a way that I think is more intuitive than what might be generated by the discriminator. All right, so the last thing I wanted to mention, which I guess is like related to ARL, but maybe a little bit more tangential, but is sort of like near and dear to my heart, is this AI Driving Olympics benchmark. So, I mean, we've seen in RL, I'm sure you all are aware, like this trend towards reproducibility in RL, and I think that's really a fantastic trend, been really spearheaded by Joël and Mila. And so we would like to treat robotics the same way. And so we've designed this set of recurring competitions really with the objective of evaluating the state of the art in not only machine learning, but any AI solutions for this simple mobile robotics task. So this competition has been run now 3 times at NeurIPS in 2018, 2019, and 2020. The 2021 ran, like last weekend. It was virtual, obviously. And it's run once at ICRA and was supposed to run at 804 at ICRA, but of course the COVID thing happened just before that, and so we weren't quick enough to be able to adapt to that, and so it just got canceled sadly. So I want to make the case to you of why robotics benchmarking, like if RL benchmarking is hard, robotics benchmarking is like even more hard, and there's many reasons for that. The first and foremost is that you can't evaluate it in some static way, in some closed loop way. Robotics tasks are complex, but you also can't randomize, like you can't fix seeds. There's no such thing as a seed in the real world of a robotics case. And so we tried to build this AI Driving Olympics competition that actually embraces this complexity as a first-class citizen. And concurrently, we've started hosting these workshops on benchmarking progress in autonomous driving. And I kind of view it as like, if we can't evaluate progress, then what are we all doing? It's like, it's sort of a prerequisite, right? So just briefly, the scientific objectives at the high level are that we have a very reproducible setup, standardized hardware environment, software and interfaces, and then it's really easy to get started. It's cheap and it's also low in terms of like time investment to get started. And scientifically, what we're looking at is really like a first and foremost, or a central theme here is this idea of sim to real, because we've built a simulator that you can randomize over, and then we have a very sort of an environment that we have control over as well, which I think makes it quite unique. And then that we want to be able to evaluate a wide range of different approaches. So this requires us to provide the resources for a wide range of different approaches. So I'm running a little short on time, so I might skip over a little bit of the details, but thinking about what actually makes a good benchmark for robotics, we want the developer to be able to do whatever they want. We want it to be able to be evaluated across the different modalities very easily. We want a seamless workflow so that you can develop your agent in simulation and then test it on real hardware and back and vice versa, or ship it around. And really, we've leveraged containerization technology with robotics to the max to try and get this workflow in a way that it's a nice user experience. And I think that this containerization technology has really been the enabler for this, for the reproducibility criteria that we really want here. So from the behind the scenes, we create this formal specification of challenges, we build these workflows, and we make these resources available. As I mentioned, everything is based on this sort of standardized interface where we have on the one hand these agents that are Docker containers, and on the other hand, we have the environment, just like we would see in any sort of standard MDT setup. But now we can ship these agents to simulator, to cloud, to wherever we want. The hardware itself is inexpensive and readily available. It's these cute little ducky bots that we made, which are in my, our design objective here was really to make the simplest, cheapest thing that we could that was still complex enough that it can do real stuff. So it's comprised, all it has is a camera and wheel encoders. And the town itself is built off of these like interlocking exercise mats, so it's completely modular. And then I think maybe the biggest and hardest part was actually to get the remote evaluation part set up for this setup. So we have these labs that are now, there's several of them across the world, where you can submit your agent and your agent will be run in this remote lab. And we have these camera system that will provide you with all the metrics and feedback of the performance of your agent. We wrote our simulator from scratch, effectively. You might ask, why on earth do we do that? And it's kind of, the answer is that there's lots of nitty-gritty details that you need to worry about and that we wanted to have full control over in terms of special things that a lot of people don't consider all the time, like latencies and rates and physics and rendering and blur and things like that. And similar to the way that I was describing when we describe the simulator as a function, the simulator is really actually a family of simulators that can generate outputs. We evaluate all of these agents over several metrics. We believe that you cannot boil down the performance of an agent like this to one single number. It is necessarily a Pareto front or a partial order. We have a bazillion logs that we can provide. We have implemented lots of baselines for people to get started. We have an RL baseline based on DTPG and also a residual RL baseline. We also have imitation learning baselines like behavior cloning and Dagger. These things work on Jetson Nano, Raspberry Pi. They're OpenAI Gym compatible, PyTorch, TensorFlow, ROS, you name it. So yeah, the objective is that it's really easy to get started and to get rolling. So we've built a whole shell infrastructure so that in 3 lines of code, basically you can get your robot up and running. So we're trying to make this AI driving Olympics become more of an Olympics. So we're looking for new events that might be interested to actually join us. At some point, I think it would be nice to have a conversation about whether a machine, like a big mobility on demand kind of challenge could be an interesting one. And then the other thing that I just wanted to mention at the very end here is that this is also being released as a massive online open source class. I believe, as far as I know, it's the first hands-on robotics MOOC that exists out there. So you can sign up on edX and you can go and buy your kit, and then you'll be able to submit all your exercises and all get evaluated in the Robotarium. That's all I had for today. If there's any questions, I'd be happy to take them.